Our section today is on an introduction to acids and bases. We've been talking about concentrations with molarities. We've been talking about how to dilute things. We've talked about volumetric analysis, so using molarities in combination with stoichiometry. So now we're going to introduce acids and bases. So we'll start with acids. These are some characteristics of them. They taste sour, so things that have a sour taste to them are often acidic. Think things like citric acid, citrus fruits. They are good conductors of electricity, so you can run a current through them. They turn blue litmus paper red. You may have heard of litmus paper before. It's a type of paper that will change color in specific pHs, whether it's acidic or basic. Acid turns red, and bases are going to turn blue here, which we'll see on the next page. And I'll give you a helpful hint to remember that when we get there, but try and remember which one is which, okay? Because when we're in lab and we're testing stuff, you need to know which paper to use. But acids turn blue paper red. Acids react with metals and metal carbonates. So, for instance, and we'll see this reaction in a couple weeks, zinc metal, solid zinc metal, will react with hydrochloric acid. What you get out of that, you get hydrogen gas, and you also get aqueous zinc chloride, okay, is what you would get out of that. But it'll also react with carbonates, so things that are, CO3 with a -2 charge. If it has a carbonate ion in it, it will also react with an acid. It reacts with water to form, these are called hydrogen ions, H+, or what you will see often is also H3O+. These two things, for our purposes, H+, you can think of the same thing as H3O+. H3O+ has a specific name. It is called hydronium. Okay, that is H3O with a +1 charge. Okay, so things that are acidic form hydrogen ions, or what we call hydronium. They are essentially the same thing. Basically, if this is in water, it immediately just turns into this guy right here, a hydronium ion. But acids contain more hydronium ions than hydroxide ions. And if you might be able to guess, then bases are going to have more hydroxide ions than hydronium ions. But there's a list of some characteristics for acids. Some characteristics for bases. They have a bitter taste. Not a lot of you have had many bitter things before. It's pretty unpleasant. But bases would have a bitter taste. One thing to note about them, they will feel slippery if you get them on your skin. What they do is they react with your cell membranes and start kind of turning it into soap. So it starts to feel slippery if you get it on your skin, even at very low concentrations. So you can tell if something's basic if it starts feeling slick. They are good conductors of electricity, just like acids, so both of these things conduct well. Bases turn red litmus paper blue. The way that I remember this, about which one does which, so if you can remember one, then the other one's pretty easy. Bases turn blue, right? B turns B. Bases turn blue. So if you're trying to figure out what sort of pH, or if it's an acid or a base, and you have litmus paper, the one that turns blue, if it does turn blue, okay, is a base. Bases are going to react with water to form hydroxide ions. Okay, so acids form that H3O+ we just saw. Bases are going to be OH- hydroxide. So basic solution contains more hydroxide ions in solution than hydronium. This is why I've been talking about concentrations, because that's what we are going to reference here, the concentration of hydroxide or hydronium as to whether it's acidic or basic. Before we get into how these sort of things form, whether something's an acid or a base, we need to talk about this equation first. This is called the ionization of water. Sometimes it's called the auto-ionization of water. What we think of water as is always just H2O. That's how we always think of it. In reality, a tiny fraction of water actually doesn't exist as H2O. So what happens is two water molecules next to each other. Water is actually in the arrangement HOH. It looks like that. But what will happen spontaneously and only every once in a while, okay, is that this one hydrogen from this water is going to detach and attach itself, okay, onto the oxygen of this other water molecule. All right, and then what we are left with, which is what I'm drawing down here, okay, what's left with on this one is just this OH, and since it lost a hydrogen, it gets a -1 charge. And over here on this side, we gained a hydrogen, so we gained a +1 charge. We get H3O+. So here's your leftover OH minus, and since this hydrogen moved over here, this is H3O+. So this happens naturally in water. However, like roughly speaking, it's about 1 in every million water molecules does this. And as soon as it happens, it can also reverse. It goes back the other way too. So it's not like once it converts into this, it stays as this. It can go back this way. So if you see a double-headed arrow as part of a reaction, that means that the reaction happens in both directions. So when this does happen, again, it's about 1 in every million water molecules, okay? You'll form a hydroxide and a hydronium ion, but they will also go back to forming 2 water molecules. So it's pretty uncommon in solution, right? It's only about 1 in every million or so molecules that does this. When hydronium's concentration is equal to hydroxide's concentration, so when these two things are equal, you have a neutral solution. Okay, we'll talk about pH later on in this unit, but it'll have a pH of 7. It'll be neutral. So distilled water, the stuff we use in lab, okay, the reason that we use it is because the hydronium and hydroxide concentrations are equal. Tap water, it's not. These two things are different. They've added some stuff into tap water to slightly adjust it. So it doesn't have a pH of 7. These two are not equal in tap water. But distilled water, they are equal. So if we have more hydronium, a concentration of hydronium greater than a concentration of hydroxide, that solution is acidic. When we have a concentration of hydronium less than the concentration of hydroxide, that solution is basic. Now, if you notice up here in this auto ionization water, okay, every 2 water molecules that turn into these two things, well, even when they're created in a 1-to-1 ratio here. It's not like I'm making more of this or this, okay? They're being created in a 1-to-1 ratio. So how do you create them in such a way where they don't come out equal like they do in water? And the answer is when we add solutes to pure water that affect these concentrations. We can put stuff into water that, say, increases hydronium or increases hydroxide, not both at the same time. And we'll see what those things are here in just a moment. Okay, so there are 2 definitions of acids and bases that we need to learn. There are really 3, but we're not going to worry about the third one for our class. So the first one is from this guy named Arrhenius. And so he's going to offer the first definition of what an acid and what a base is. It's the most straightforward, simple definition. And you'll see what these things look like and how to identify them pretty clearly. Arrhenius says that a substance that contains hydrogen and ionizes to produce hydrogen ions in water is an acid. So we call that an Arrhenius acid. So it has to have hydrogen in it, and when you put it into water, it has to come apart, okay, to produce hydrogen ions in water. So the classic example here, HCl, this is called hydrochloric acid. We'll learn why it's named that. Some of you may already know that, but we'll learn why it's named that in the next section. HCl is actually a gas, normally, but if you bubble that gas into water, it doesn't stay as HCl. It breaks apart into hydrogen ions and chloride ions. Okay, and what you might remember from just a few minutes ago, H plus is really the equivalent of hydronium. Okay, so by bubbling this gas through water, what we are doing is increasing the hydronium concentration. Okay, that's what we do. And so this is going to make the solution acidic. I'm not adding any hydroxide ions, right? This didn't do anything to increase the hydroxide ion concentration. All it did was increase the hydronium. A base, then, he says, is a substance that contains a hydroxide group and dissociates to produce a hydroxide ion in water. So this one's pretty easy because what are we looking for? We are looking for hydroxide in the formula. Okay, so the formula needs to have a hydroxide ion in it. The standard example here is NaOH. This is sodium hydroxide. And it breaks apart into water, right? It's got to be soluble. It's got to be able to come apart into whatever this ion is here. Sodium ion doesn't really matter. The thing is that the important part here is that it dissociates into also hydroxide ions. Okay, so that OH, the -1 charge, that is going to increase the hydroxide concentration, which is going to make something basic. So this is the first definitions here of what an acid or a base was, right? Arrhenius said an acid has hydrogen in it, and when you put it into water, it creates hydrogen ions. He said a base contains a hydroxide group, and when you put it into water, it produces hydroxide ions. And this was a good start for definitions. This was the first and initial one, but it wasn't enough, because when we started testing other substances, we found that some things didn't really obey Arrhenius's definition, but still made something acidic or basic. The big reason here why we needed another definition and not just Arrhenius's definition is because things like NH3, which you should remember from first semester, okay, that is ammonia. Ammonia is a base, and this one here is called sodium carbonate. Both of those things, there's hydrogen in this one, but it's not going to dissociate into hydrogen ions. And there's no hydroxide or hydrogen in sodium carbonate. Both of these things were basic. And so if we're looking at the definitions here provided by Arrhenius, right, these two kind of broke those rules. So this clearly wasn't enough to explain what was going on. We needed a better definition. We could test ammonia. We'd put the red litmus paper into ammonia water and it would turn blue, which told us it was basic. And these definitions weren't ownough to explain that. So we needed a new definition in addition to Arrhenius's. So that's going to be these two guys, Bronsted and Lowry. Instead of talking about hydrogen ions and hydroxide ions, they are going to put it in terms of donating a proton or accepting a proton. And the thing to think about with this is that hydrogen ions, right, H+, versus H. Well, a single hydrogen atom has got one proton, typically 0 neutrons and 1 electron. Okay, most hydrogen atoms do not have a neutron. It's just 1 proton and 1 electron. A hydrogen ion, well, it's lost the negative charge, so really all it is just 1 proton, right? There are no neutrons in it, and if it's got a charge, there's also 0 electrons. So really, a proton is the same thing as a hydrogen ion. All right, and Bronsted and Lowry are going to put it in terms of protons. And so they say an acid is a substance that donates a proton upon dissolution in water. And something I haven't mentioned here yet, if a compound starts with H and then goes on to something else, that is highly likely to be an acid. Okay, so here they're just using some generic acid. X is not a real thing. It's just saying that this H here, which we are really thinking of as a proton instead of a hydrogen, plus water, is going to produce this hydronium and this X anion, whatever X is. It will have a -1 charge because it's losing the proton, the +1 charge here, to the hydronium. So HX donates this proton in the form of what looks like a hydrogen to water. Okay, and then they came up with another term here for this X anion over on the side. Okay, they're going to call this the conjugate base. And the reason being is that with this negative charge, it could potentially pick up a proton and accept it, which we'll see here in a minute is the definition of a Bronsted-Lowry base. Now, overall, these two look very similar. This definition here seems pretty similar to the Arrhenius definition, because after all, it's still H something plus water, giving us more hydrogen ions or hydronium ions plus some other anion. That looks pretty similar. It's when we get to the definition of the base here in just a moment that it's going to be a little bit different. But know that we refer to HX in this situation as an acid. We refer to X with the -1 charge as the conjugate base. It's always the thing getting produced over here. Okay, so a minute ago we were saying things like ammonia and sodium carbonate, Na2CO3, those were basic even though we didn't have an explanation for it. And so Bronsted and Lowry, again, putting it in terms of protons, found a way to explain how these things were basic. They say a base, Bronsted-Lowry base, is a substance that accepts a proton upon dissolution in water. So what's happening here? Ammonia is not donating a hydrogen off. Instead, it's going to add another hydrogen, or in this case, right, we'll use the word proton, onto it. So ammonia plus water, what we get, okay, is NH4, ammonium ions, and hydroxide ions. What I want to do real quickly underneath this is draw this out. So here we've got an ammonia molecule, okay, plus water. All right, and what we're going to get out of this, one of these hydrogens in the form, right, again, we're thinking of it as a proton, is going to pop off and attach to the nitrogen. So we get this nitrogen with 4 hydrogens now surrounding it. Okay, that has a positive charge. Drawing this correctly. Plus, and then what's left on the water is this OH, which, since it lost a proton, has a negative charge. Well, this guy right here, that's hydroxide, right? And in order for something to be a base, it needs to be that when you put it in water, it produces hydroxide. Well, this was a way of producing hydroxide even though the compound itself did not have a hydroxide ion in it. Okay, so this explains why ammonia was a base. And just like we had conjugate bases a minute ago, we also have conjugate acids. So NH3, we would call that a Bronsted-Lowry base. And then the NH4, the ammonium ion, which is on your ion sheet, okay, we would call that the conjugate acid. So we have bases with conjugate acids, and then on the previous slide we had acids with conjugate bases.